Okay, it's a wonderful Saturday here in Cape Town, almost summer, lovely weather out. Saturday here on the University of Cape Town campus. Now, for quite some time I wanted to put together this video series just on using R for biostatistics. Now, in my research unit, R is not our language of choice. We use the Wolfram language most of the time. We also use Python quite a bit. R is something that we use from time to time. We have many students come to us and they're already working in R, many international students working R, and R is actually, it's a language for statistical analysis, and it is a fantastic tool for biostatistics. Don't get me wrong, I think it's probably one of the best. And we do use it under these circumstances, as I mentioned. So I've always wanted to put together these videos on the use of R for biostatistics. So this first video is actually going to be quite long. I just want to give you this whole introduction to R in one quick go. Now that makes it a bit difficult because I can't tell you everything in one video, and it really gets long, and it is a long video. But I really want you to get an understanding of what R can do for you as far as biostatistics is concerned, and if you want to use it. So we're really going to run through the installation of R, how to create data, how to create simulated data, how to do descriptive statistics, how to visualize your data, and then how to analyze your data. But even before all of that, I'll just show you how to code in R, so just get some feeling of what this functional type language is all about. So really R, fantastic language for statistical analysis, for biostatistics, and I hope you enjoy this very long first introductory video. Now, I've already made a few others just on some visualizations, some on logistic regression. Please find them. The data files that I'm going to use, they're going to be available on GitHub, so you can just download them. I'm going to tell you all about RPubs, where you can publish your documents as HTML documents. Really all a fantastic, powerful tool, R and RStudio. So I really want you to enjoy this. Let me know in the comments if you see anything that you want more videos about. We use R, as I mentioned. You can do anything in R as far as biostatistics is concerned. So really, if you are interested, just let me know in the comments and I'll make more videos. And especially for all the international medical personnel that do visit us in our unit and who want to use R, no problem whatsoever. So really the first thing that I want to talk to you about is just the installation of R. Now, we mentioned R is a programming language specifically based on doing statistical analysis. And the way to get R, if you are on Windows or Mac OS, is just to go open your favorite browser and just type in R spaced CRAN. And we see CRAN as the Comprehensive R Archive Network. So if you just type that in, the first link that you're going to see probably is cran.rproject.org. And if you go there, this is what you're going to see, a very austere, old-fashioned kind of website, but everything is there for you to download. And you can see there Linux, Mac OS, and Windows. And if you click on those, you're going to get a file. You're going to download it and install it as you would any other program. Now, you can install or get at least the files to install R for Linux here, but if you're on a Linux system, I would really just suggest that you use the package software that comes with your distribution. There is going to be a type of app store for your distribution, and R would usually be there. It's usually called R-base or R-core. All the distributions give it a bit of a different name, but if you search for that, you are bound to find it, and it's much easier to install it through your distribution than it is from downloading a package and installing here, unless you know what you're doing and you are familiar with installations on Linux. So once you've installed that, that is just going to give you a user interface that really just allows for typing at a terminal. And what we really want is a graphical user interface. So after installing R, I want you to search for RStudio, and you can say RStudio or Space Studio. First one that's going to come up probably is rstudio.com. Let's have a look at that. And it's in a development environment that will see where your installation of R is on your system, and it'll use that, but in a nice graphical user interface, and I'm going to show that to you shortly. Here you can learn a lot about RStudio though. There are even paid versions here. We're not interested in that. We're just going to download RStudio there. That's the free version, and you're going to install that. You can read about some of the packages that the RStudio company, if I can call them that, to develop. You see R Markdown, Shiny, Tidier, Knitter, ggplot2. They're all going to be there available for you free of charge, but you can look at those packages. And really the way that R works, there is this base language itself, and that is what you downloaded from CRAN, but it is extendable. In other words, people can come and write extensions to the language that just makes your life so much easier. Shiny, for instance, is something that you can use to develop programs. Tidier, very nice to wrangle your data. If you bring data in, you can really clean it up nicely. ggplot2, they're a very fantastic plotting library. Now I'm going to show you can plot just with base R. You can create very nice plots and graphs, but ggplot2 can give you even nicer looking graphs. And there are really thousands of these packages, very easy to install, very easy to then just use in R, but they just make the abilities that R has to help you with your statistical analysis is just so much bigger with these thousands of applications or packages that you just then add to R. Another beautiful thing of R is this rpubs website from RStudio, rpubs.com. And if you are here on rpubs and you refresh your web browser every now and again, you'll just see new files coming up. If you're in RStudio and you create a file, which I'm going to show you, you can upload it to this cloud website and everyone can see it. So it's very nice if you want to collaborate with people. People can see your work, you can collaborate with others, and you can also just look at other people's work here, and it's a brilliant place to learn a few things. So for instance, a lot of the work done in my unit, we do put out here on rpubs. And this video is all going to be about introducing R for biostatistics, and the file is already being created and it lives right here on rpubs. So if you go to this Jean H. Klopper, that is rpubs.com/JUANHKLOPPER, and then /intro to R for biostats, all those words with underscores between them, but just go to Jean H. Klopper and you'll see all our files there. And this is the file that we are going to create. Let me hide the toolbar, give us a bit more space. And this is what a document looks like that we created in R. It was very nicely formatted here. You see that we have a title here, a subtitle. We see a table of contents, and we can even click on those. That is going to take us down to this. We put a nice logo in there. And another subtitle sections here with nice text written in. And a whole document that I created for you, and this is what we're going to run through. I'm going to talk to you about the libraries, some simple arithmetic, how to create lists, what computer variables or objects are, how addressing works. We're going to talk about distributions, descriptive statistics, visualizing our data, tables, which are just data frames that you can see that as very fancy spreadsheets, and we can import spreadsheets as tables. How to import our data, how to inspect the data, how to select out of your data only the things that you want, descriptive statistics on this new data of ours, visualizing this new data, and a bit of inferential statistics. So I'm going to show you all of these. You can just look at this document here, but I'm also going to show you how to create this document. And this video is really for you to decide, will R solve your problems? Would it be a good tool for you to use? So I'm not going to go into too much detail. I mean, this is going to be a long video, but I just want to give you a nice introduction for you to decide, do you want to get into R? So you can come and have a look at this file, but this file is also going to be available on GitHub. And here we are, my GitHub site. So that's Jean Klopper, that's without the H. And then we have /R_statistics. So all the files that I've created so far live on this GitHub repository, and you can just clone or download it. If you don't know how cloning works in Git, you can just download the zip file, and it's always going to give you all of these files. And if we look down here, we can see quick intro to biostatistics.rmd. That's the actual file, and if you download that, you can open it in RStudio and you can see the actual file. Now that you've installed R and RStudio, you open RStudio. This is not what you're going to see, because this is the file that you've just seen in rpubs. What you'll see is a blank slate, and what you can do is just go to File, New Script, or just under File you see the little plus sign there, R script. Now that is certainly one way to enter data into R. I can type in 2 + 2, and if I hold down Control or Command and hit Enter, you'll see the console opens up at the bottom, and you see there 2 plus 2, and you see the solution 4. You also see this little 1 inside of square brackets next to it, and we'll come to that a little bit later. So this is one way to work with R. You can also work right down here in the console. I can type 2 plus 2 down here, and instead of hitting Control and Enter or Command and return, I'm just going to hit Enter, and we see the 4 appears right there. The difference between this console and this window up here is this console is not going to save anything for me. I can do some quick calculations there, but it's not going to save anything. This file up here, I can save that file and I can reopen it, and everything I typed would be back there. So these are the two main parts, but let's explore a little bit more. On the right hand side, quite a few other things. We see an environment here, and if we start storing things in our file, those are going to appear here. A history of what we've done before. Connections we're not really going to be too concerned about in this introduction. The importation of data sets, we're going to do that right in the code. We won't use that. Very importantly, the tiny little right bottom here. Files is just going to show you the file structure of where you are at the moment. Plots, if you were to make any plots in your code here, it's going to appear in this little section down here, and you can even export your plots as different types of images, JPEG and PNG, etc. Packages, very, very important. This is where we're going to go when we want to install packages. Remember I said thousands of packages exist, and they extend the base R to allow us to do a lot more. And we're going to click on install, and then here type in the name of the package we want to install, leave everything else as it is, and just click install. And those packages will then be installed on your system, and you can just import them. And I'm going to show you how to do that. Every time you have a new file, you can just import all the packages that you have installed. Help, absolutely fantastic. A whole set of documentation, and I'm sure if you had to print all of this out, it would be a very thick textbook indeed. So all the documentation there for you, and viewer is going to give us a view of certain things, and we might get to that right at the end, we'll see. So definitely, this is where you can go. You can also then just click on the Save button there and save this file. That is not what I want to talk to you about, though, in this introductory session. I want to talk to you about R Markdown. So if I click on the little plus sign and we go down, the third option there is R Markdown. It's going to say the following. Do you want this to be a document? Do you want it to be a presentation? And that is like PowerPoint. Shiny, remember I said that's an application, or there's even some templates that you can choose from. So we're going to stick to document, and you can give your document a name. Let's call it test. You can put in your name there, and then you can say the default output format, you want that to be a web page, and that you can either export to your own website or upload to RPubs. Do you want the export to be a PDF, or do you want it to be a Word document? So lo and behold, you can write all your code and you can export it as a Word document or as HTML. Now you can change this after the fact, after choosing this. So just leave it at HTML, no problem there whatsoever. And this is going to open up this default new file here, which you can then go and save as well. So if I were to click on save, it's going to open my folder structure on my hard drive, and I can decide where to save it. The first bit of code that you'll see at the top is these 3 little minus signs, and it ends on line 6 with another 3 little minus signs, and this part is called YAML, just another markup language, and that just tells RStudio what to do when you do export it eventually to a Word document, to a PDF document, or to a HTML document. It just gives us that bit of information. And I'm going to show you how to change that a bit later. Now here you see the 3 tick marks, tick, 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 and then curly braces, and then R, and then a space, and then setup, and then a comma, and then include equals false, and then knitter, K-N-I-T-R, and 2 colons, options, chunk, dollar, set, echo equals true, close, the 3 little tick marks. And that is called a code chunk. So if we go back to just this normal file that we did, to the R script, everything you write here is code. But if you do an R markdown, you've got to put your code inside of a chunk like this. Everything outside of a chunk is going to be viewed as normal text, as you would have on a web page or a Word document or PDF. So you've got to embed your code inside of a chunk, and I'll show you how easy it is just to create a new chunk. And when we go to the right hand side here, you can click on this little wheel and it's going to give you a bunch of options for this chunk, and I'm going to show you all about that as well. What we see below here though is now just normal text. This is outside of a chunk, and you see there's two little hashtags here, or pound signs or symbols. And because we are exporting this to HTML as it stands, that tells a website how big this text should be. Or if we export it to PDF or Word, how large also this text is going to be. And these little marks here, these little hashtag or pound signs, you get from one of them all the way up to 6 of them. 1, 2, 3, 4, 5, 6 of them. 6 being the tiniest little subtitle, and just 1 being the largest, that's a title. But you see title up there, that's just going to put test in this biggest form it can possibly be. Now I can change it here, even though we put in test, doesn't matter, I can change it here to something else. Something else that is by default going to be H1, or just the 1 hashtag. And 2 hashtags means slightly smaller, that's H2. Now, or header 2, a second size header. And then you just get the normal text. You can put in hyperlinks by just putting them inside of these less than and greater than signs. You see more code chunks there. I'm going to show you all about these. So we can mix this text, we can mix different sizes of titles and subtitles, and we can create this research document. So just imagine this, you produce a document of statistical analysis, but in between you can also just write normal text as you would any normal text editor like Microsoft Word. You can even do spell checking by hitting F7 on your keyboard or going up to Edit, and all the way down the F7 you can see check spelling. So we can check your spelling. Really phenomenal piece of software, RStudio. It is basically a web browser in the back end, the parts that you don't see, but the parts that we do see here, the graphical user interface, fantastic to work with. So again, as I said, imagine you can put together this research document that you can share with others. You can export it as HTML and share that, put that on your website. You can share it on RPubs, or just print it out as a PDF or Word document, share that with your collaborators. And it's got mixed code and the results of that code. So your statistical analysis, your plots, your graphs, and just normal words in between. So it's a beautiful research document. So let's just go to the document that we created. So what I do is when a new document like this is opened up, I would change a bit of this, and I'll show you now. And I'll come right from here, right to the end, select all of that and delete it. That's how I like to start. That was just a bit of template that RStudio opens for you just to show you around. But this is where I like to start. I know that I'm going to have a nice big header there. That's from the title in my YAML. And I'm always going to start with a subtitle. So that's 2 little hashtags or pound signs, and now I can start typing. Because if we look at the document that we're going to work on, looks slightly different. I've added a few things and I'm going to show you all about those, but this is where it really started with these 2 hashtags, and I have introduction there, and we start writing the introduction. But I'm going to show you all about all these changes that I made, just so that you're familiar with them and you can incorporate them in your own documents. So let me show you how I like to set up my documents. So here's our title. So I just changed it to a quick introduction to R for biostatistics. The author is this there, but then I change this output. So if we looked at the output before, it just said output HTML and it had the date there. So I took the date out, and then I put output colon, and then on a new line HTML document, and then TOC colon space 2. That is going to give us a table of contents, and the number sections I want false. If you put that to true, it is just going to give you 1, 1.1, 1.2, then 2, 2.1, as your subtitles, subtitles, etc. go down. And that's not what I want for my document, but you can certainly put that to true. So this would be a default for me. Now the first thing I did here is, just for the sake of this introduction, is just I created a code chunk. Now the way that you can create a code chunk is just to go up here to code and say insert chunk, but you can see the keyboard shortcut there. On a Windows and Linux machine that's going to be Control-Alt-I, and on a Mac OS that is going to be Command-Option-I. So let's do that. I can just come in here. There we go. Let's hit enter or return, create a bit of space there for ourselves. Again, there we go. I'm going to hold down Control-Alt or Command-Option and hit I, and you see there we have a code chunk. So I can start writing my code inside of this chunk now, and that would be completely analogous to the way that we just entered code here in a normal script file. And we can run this file and that would execute for us line by line. We see line 1, number 1 there is going to have 2 plus 2. That's going to execute and give us a 4. And then line 2 and line 3, etc. But here in an R Markdown file, we have to put it inside of this chunk. Now if I go to the little gear icon here, immediately you see I can give this chunk a name. And let's give this chunk a name, and just call it name. As I type name there in the tiny little block, you see name appeared there. So the first thing after this R and a space is going to be the name of this chunk. And it's very good to give your chunks names, because when you give this file to someone else or you look at it weeks and months down the line, you can remember what that code chunk was all about. Now you can also decide on the output. Now whatever you do here is going to be reflected by some code that is generated on the side, and after a while you get to learn what this code is all about, and you can just type it in there and not come to this little gear icon. But you have a few options here for output. You can say show output only. That means when we do create our Word document, our PDF document, or an HTML document at the end, the actual code is not going to appear, only the output of the code. So you can imagine a situation where all you want to show is just some words and text and headings and subheadings, and you want your graphs to appear. Not the code that generated the graph and the plot. You would choose that. Show code and output, and that is going to show the code that we write and the output. Show nothing but run the code. Sometimes we have to execute some code, get some results, which are then used later, and we just want to run those, but we don't want those to appear in the document. You can choose that. And then show nothing and don't run the code. Don't know really why you would use that, but there probably are scenarios which you can. Now you can also choose not to show warnings and not to show any messages. Sometimes when we import packages, they're going to overwrite some of the base functions that are inside of R, or they're going to overwrite each other's functions if we import more than one package, and it'll give you some warnings and some messages, and those can just be a bit annoying, especially if you know that they're going to appear and you know that it is going to happen and you work through that. It's not a problem for you. You can just untick those and nothing will happen. Use paged tables, we never use in my unit, and use custom figure size. You can certainly look at that if you want to. But you notice when I untick those, we had comma there, and then message equals false and warning equals false. As I said, after a while you can just start typing those yourself. If I hit apply, we can start writing here. Now what we've see down here is exactly what we are busy creating here. I called this one comments, and I said include equals false. I don't want this included in the document that is actually going to be produced in the end. Now here's some actual code, but you can see the beginning of this code has a hashtag or pound symbol. That has nothing to do with the heading and the size of the heading, because this is inside of code. Inside of code, inside of a code chunk, it means something completely different. It is actually a warning to R itself that this is just a comment line. Everything to the right of this on that line is just human comment, and R will totally ignore it. So if we go back to just a normal script, I can do the same here and say this is a line of comment, and that's it. And it's going to be completely ignored when the execution goes line by line. It's completely ignored. And again, it's a very good way of just leaving some information for your future self or for your collaborators, that if you want to let yourself know, someone else know what this was all about. So do make liberal use of naming your code chunks and putting these lines of comment in. Now, why name these code chunks? Another good reason is if you go right here, right to the bottom, and you click on that, your whole document actually opens up. And because I've named every chunk, you can see there chunk 52 has mean age by group. So it's very easy for us to go find something later on that we were working on. Instead of scrolling down this long file, we can just quickly go look for that. And you see here in darker text, it's tiny here on the screen, I hope you can see it, is all the headings and subheadings will also appear here nicely tabbed out so that you can see how this document was put together. And if I remember that I quickly wanted to go to addressing again, I can just click on it and it'll jump to that section. But this only works really if you name your chunks, and it will automatically see these symbols here that for your headings. It'll automatically see those, but name your chunks. Otherwise it's just going to say chunk 6, chunk 7, chunk 8, and you're not going to know what it's all about. So just get into that habit. I prefer to do that. Now, just in this last little bit on setting up this document, 2 more things. And that is, if we are going to produce an HTML file, we can actually bring in some cascading style sheets. And I can write normal HTML just by putting things inside of these less than and greater than symbols. So I'm just going to put a bit of a style in. And so my opening style HTML tag there, and then my closing style tag there, and then anything in between is what we actually want. So the type is text /CSS cascading style sheets. That's just normal. We just put that in. And then all I want to do is heading 1, heading 2, and heading 3. So that's akin to the single hashtag in markup language, the 2 hashtags and the 3 hashtags. So that's the very big text, the title text, the subtitle, and subtitle. It just gets smaller. And I've just given them each a color. The color is an argument there, and that goes inside of the set of curly braces, colon then, and then in hexadecimal code, starting with a hashtag, the value. So that's a navy blue, that's a gold, and that's a slightly lighter sort of navy blue. So that gives us a color. And you can bring in all sorts of other things. If you know HTML and you know cascading style sheets, you can really go to town on your web pages and really change it up and make it look all fancy. Last thing for this section before we start with the actual introduction is you can also bring in some logos. Now, one thing I want to say about that is that we are going to save this file somewhere on our hard drive or on our solid state drive. We're going to save it somewhere. And what I like to do is all the files that I work with together with this notebook, this RMD file, this markup file, I store in the same folder on my hard drive. Everything lives in that same folder, and that means I don't have to go type in the long address bar, C:\/ my documents / etc, etc, and on macOS it's going to be different. I keep it all in the same folder, and then I do the following. Now remember, this R setup includes this false that was automatically inserted, this knitto options chunk set echo equals true. That was there automatically. What I like to add there is this little line of code. Set WD, get WD. Once I've saved this file on my hard drive, I can let R find out where on the hard drive this actual file is by this text here. Get WD, open, close parentheses. Get working directory, open, close parentheses. That is actual R code. It tells R, go find out where I am at the moment. So you have to save the file first, and then you can run this get WD, and it's going to return this long string of C:\/ or macOS is a bit different. So it knows where it is, and I use that inside of another function. So you don't know a lot about functions at the moment, so just roll with it. So I've got set WD, and it's got its own set of open and closing. You can see the open close parentheses there, and this get WD with its open close parentheses lives inside of the set WD's open and close parentheses. Now these things are called functions, and what goes inside of these parentheses are called arguments. So this get WD without an argument, this is open and close parentheses, that is an argument inside of the setWD function. So I'm passing this argument to the setWD, and that just means that long address that getWD got for me, it's passing that as an argument to setWD. That tells this file we are using this little part of our hard drive where this notebook is saved, or I should say our Markdown file is saved as the default. So anything that lives inside of that same folder I can just reference directly, because this file knows where it lives now. And now I've got this nice little PNG here. We see it there. It's called KRG Elegant Logo for Light BG.png. It's a PNG image file, and I don't have to put the long address to get to that C:\images, wherever on your C drive or whatever drive it is. Because we've used the setWD, this file knows where it is in the world. And because this file and this PNG lives in the same folder, I can just type the name of the file. And if I had a spreadsheet file, I would also save it in that specific folder. That is the way I like to work. It just makes life so much simpler. And the way that you get a logo into your Word document in the end, or HTML document in the end, is by this exclamation mark, open and close square brackets, and then in a set of parentheses you just type the name of your image file, .jpeg or .png, whatever it is. And now when we export this, that actual logo that you saw before, that will be there as well. So that's it for the how to set up, the way that I like to set up my files in my research unit. And it's a structure that we use, and this will be the default, and you can actually just save this as a template and just open that template every time. Next up, we're just going to start then looking at libraries. So let's talk about these libraries. Now all I'm going to do is just a console here at the bottom. I'm just going to click this little minimize button. You see minimize and maximize. I hit minimize, it goes away. I can hit maximize again, it'll come up. So let's just talk about libraries. I mentioned before that is just these packages that allow for the extension of base R so that you can do so much more. The ones that we're going to talk about we're going to use here are these 5: Tibble, Reader, dplyr, DT, 4 of them. And they're not going to be there by default on your system, so please go to Packages and then Install, and then you can type them in one by one: Tibble, Reader, dplyr, and DT. And just install them one by one. That's the safest to do, and they'll be available. They are on your system now, but every time you run a file, you've got to actually just tell R to go use them. And the function for that is just library. Every function is followed by a set of parentheses, and inside of those parentheses we put 1 or 2 or 3 or more arguments. We separate those arguments by commas, but each of these will have one argument. That's Tibble, Reader, dplyr, and DT. And you just type their names as it appears there. Now to run a code cell, we've got to actually run these. So if I run this first one here, nothing is going to happen whatsoever. I just want to delete this one, so I don't save it in my system. Let's just neaten things up. Single open line there. You can just click on this little run button and that will run the code. You see a little green line appear there. And let's just run this one. There's nothing in there. It's just comments and nothing is going to happen. This one actually has something in there. So let's run this code. So the knit options have been set, and the set working directory, get working directory has been set up. So I can just click, as I said, on this little run button. Alternatively, I can hold down Shift, Control, Enter, or Shift, Command, Return. And if we do that, if we're just inside of the cell, that is going to execute as well. So that's just the shortcut, keyboard shortcut. Shift, Control, Enter, Shift, Command, Return. And all of those libraries are now part of R, and I can just use all the functions that are inside of those libraries. So let's start with simple arithmetic. And so I've got a bit of text there, simple arithmetic. I've written a few lines of text. What I actually would love for you to do is to go on GitHub and download this file for yourself and start making your own notes. So go in between these sections, make a little space for yourself, and just type in your own code, my own notes, and just start doing that throughout this. I've kept the notes very sparse in this document because I'm just talking about all of these things, but I would love for you just to download this document and just type in your own notes in between. So addition we've seen before, very simple, 2 plus 2 plus 4. I'm going to hold down Shift, Control, Enter, Shift, Command, Return, and we see execution there. It's 8. And again, this mysterious little 1, and we're going to talk about that. Subtraction, it's just like a normal calculator, very easy. Multiplication, remember we don't have a multiplication sign on a keyboard, so it's Shift 8, that little star symbol on most keyboards. Let's execute that. We see the answer is 24. Let's do a bit of division. 3 divided by 4 is 0.75. Powers, we use the little caret symbol, Shift and 6 on my keyboard. 3 to the power 3 is 27. Now we can also mess about with the order of arithmetical operations. Remember, we do division and multiplication before we do addition and subtraction. So if we want the addition to happen before the multiplication, we actually have to put that in parentheses. So this says do the 2 plus 4 first, and then multiply by 3. So that's 6 divided by, multiplied by 3, that's 18. Otherwise, if I didn't put those, it would be 4 times 3, which is 12 first, times 2, plus 2 is 14. But we're going to get the 18 here because we forced that. Just some other functions, something that we might use a lot in statistics, just the exponent, Euler's number. E to the power 1 actually gives me E. And E, Euler's number, we write in R as EXP, exponent. And if we raise that to the power 1, we're actually going to get Euler's number, 2.718282. So we see there 1, 2, 3, 4, 5, 6 decimal places. Log base 10 is log 10 is the function, log 10. And I pass an argument to it. In this instance, it's 1,000. So I'm saying what is the log of 1,000? And the log is base 10 here. And 10 to the power, what gives me 1,000? Well, 10 to the power 3, so log base 10 of 1,000 is 3. Now, the normal log function without the 10 there, that function, will give me by default Euler's number, E, as the base. So this is actually the natural logarithm. But I can actually specify the base. So I could say here base equals 10 as my second argument. So let me do this properly and show you. If I start typing log and then 1,000, the base is going to be E, it's natural log, but I said I can also say base equals 10. So what we have here are two arguments for the log function. 1,000, the first argument, it expects the number for which it wants to calculate the log of, and then comma, a second argument. This argument is called a keyword argument because we're actually specifying a name for this argument. We didn't give this first argument a name. I didn't say number equals 1,000. That would be wrong. The way that this code was written is the first argument that it expects is the number that I want to calculate the log of. So I can just write it. But then thereafter, there are some keyword arguments. And keyword arguments you can put in different order. You can put one in front of the other, it doesn't matter, because they have names to them. The first one that it does expect though, and that's the way the code was written, you can't do anything about that, was the actual number. And so that's not a keyword. And sometimes there are 2 or 3 or 4 of these which are just expected in that order. You can't swap that order around. But once you get to the keyword arguments, you can swap their order around because they've got names and R won't get confused to what you're trying to do. So one of the keyword arguments for the log function is the base. And we say base equals, and yeah, I said exponent 1, so that is just E. So that is just the default. But what I like to do after a comma is hit enter or return, because I like to put my arguments, most of the time I love to put them one following the other on its own separate line. And you can see the nice little indent that RStudio does for you all by itself, and that's fantastic. And we see log, the natural log of 1,000 is 6.91. Next up, we're going to talk about lists. So let's talk about lists. We've put in single numbers, we've done some arithmetic, but what if we want to save a bunch of numbers or something else? And we call those lists. And we create these lists inside of R. We sometimes refer to these as vectors, but just let's call them lists. We put them inside of a function called C, just C, for concatenate basically. So I'm going to say C, and then I'm going to pass the list of arguments, and the arguments are just going to be values. So let's imagine these are systolic blood pressures of patients. So a patient had 120, the next one 120, the next one 110, the next one 130, the next one 140. So those were the 1, 2, 3, 4, 5 systolic blood pressures, and I'm just type them all in and I put them inside of, as arguments inside of this C function. Let's run that. And we get back the 120, 120, 110, 130, 140. As simple as that. Now we needn't just stick numbers in there. Here you can see that I stick actual words in there, or I can even put sentences. These are called strings. And strings go inside of quotation marks. Always, always, always put words inside of your code in quotation marks. They're called strings. So here I have pneumonia, ARDS, and bronchitis. And I can run that, and lo and behold, I get back my pneumonia, ARDS, chronic bronchitis, still with this mysterious little one at the end, in the beginning I should say, and we're going to get to that. Now you can think to yourself, well, it is a bit unfortunate. Do I have to type in these numbers over and over and over again if I want to reuse them? Well, fortunately, no. What we can do is create a little space in our computer's memory, and we can store this in that space. Now this little space in memory needs a couple of things. That's the way computers work. First of all, it needs to have a name. I have to give that little space in memory a name, and that's called a computer variable name. So what we've done here is given it a name, SBP. And please give it a descriptive name. Again, you give your code to someone else, you look at your code, months or years down the line, you sort of want to give it a name that means something to you, that you can just look at it and say, oh yeah, that's what I wanted, that's what I was referring to. So SBP for systolic blood pressure, that works for me. So I'm going to call this SPB, and then that's the little name, the computer variable for that little piece of memory. And then we're going to store something inside of that piece of memory, and that thing is called an object. And that object has a type. So if we see here C with 120, 120, that is a list. So we are putting a list object inside of your computer memory, and we give that little bit of memory a name, a computer variable name called SBP. In basic terms, this is what is happening. Now you'll see this little weird thing, less than and minus. Now you are very welcome to use equal. Now, equal in a computer language means something very different to equal in mathematics. The equal symbol, a single equal symbol, means assign. It says, take whatever's to the right of me and assign it to whatever's to the left of me. So here we have a list object of integers, and we are saying assign this to whatever's on the left, and on the left it recognizes this characters that you typed, and it knows that this should be, or knows that this should be a computer variable name. So it's an assignment operator, this equal sign. It's not an equal sign, it's an assignment operator. So we're going to store that inside of SBP. Now, how do you choose your names? As I said, please choose them that it means something to you. Don't start it with illegal characters such as spaces or numbers. Never put a space inside, because it's going to be seen as two separate things that you're trying to enter. Just stick to the basics. SBP works for me. Now, it's stored in my computer memory, this list object, and I can just recall it by just typing its name. So I'm typing in the computer variable name in this code chunk, and I can execute that, and it's now going to give me back those numbers. 120, 120, 110, 130, 140. So I don't have to retype them ever again. They are now stored in this piece of memory in my computer under this computer variable name. This object is stored there. So let's create one instead of typing it in. Something very useful that I use every now and again is this sequence function, SEQ. That just reminds me, I forgot about this little equal sign that I said that you could use here. So you can use this equal sign, but it's more common in R for a variety of reasons to use this little assignment, little symbol. And to very easily get that is to hold down Alt or Option and hit minus. That's the keyboard shortcut, Alt minus. And it sort of shows what it's doing. The arrow is pointing to the left here. It's a little stabby arrow. And it is clearly trying to show that take whatever's on the right and pass it to what's on the left. It's a better idea of, a visual idea of what this assignment operator is. So I like using it instead of the equal sign. As arguments though, keyword arguments, with the name of the argument and then its value, there we put the equal sign. So we have here, this SEQ stands for sequence function. And it's taking here 3 keyword arguments, from, to, by. From says start at 1, to says where to end at 100, and by is by how many jumps. So 1, jump 2 is 3, jump 2 is 5, jump 2 is 7, and that's what the sequence does for me. I don't have to put the by. If I don't put the by in, the default is 1, so it'll always go up in 1, then it'll be 1, 2, 3, 4, 5 until 100, but I want to go up in steps of 2, so I put the by keyword argument in there. Again, I'm assigning it to this computable variable, and now you see a different naming convention here. I can actually string words together. Remember I said no spaces, and I can use dots. This is called snake case, because you can snake the words together. The proper snake case is actually just making these underscores. That really is snake case. So I could have called this the patient numbers and just put these underscores in between, no spaces. But I like the dots when I work with R. It just sets my mind that I'm working with R. If I work in Python, I use underscores. If I work in Julia, I would use underscores. If I work in the Wolfram language, I will just not use any spaces or dots or underscores. Every subsequent word will just be an uppercase letter. So this is what I would normally do inside of Wolfram language. Patient, the first one always lower case, and then every subsequent word, so that I can read it as a human being, goes into uppercase. So it's just the way you can use all of these work in all these languages. But I just like to use these different things, and it just reminds me in what language I'm working in at the moment. So for R, I like these dots in between. And then I'm just going to call that computer variable, and we're going to see what it looks like. There we go. 1, 3, 5, 7 as promised. Now we can see something else. Remember the mysterious 1? Now we see a 25 and a 49. And that is a beautiful segue into the next section, and that is addressing. Because I have a list object here, every object actually has an address. Just like you live at a certain address, every element inside of a list has an address. And it starts at 1. R starts counting at 1, whereas Python starts counting at 0. So just remember, R starts counting at 1. So that's element number 1. The 3 is element number 2. This 5 is element number 3. And 4, 5, 6, 7. And what R does when it shows you the calculation, it just says the first one on this line, and you might have a much bigger monitor, you might have a much smaller monitor as far as the resolution is concerned, so you might see more on that page, on that line, and you might see less of the elements on that line. It just says this first one on this line, what element number is it? So this 49 is element 25, and this 97 is element number 49. So it's just a small little indication of, please remember that all of these have an address. Addresses go in square brackets, and I'm just telling you that the first element in each of these lines, I'm just giving you their addresses. That's just the default setup. So let's have a look at addressing. So let's talk about addressing. And remember I said that always goes inside of square brackets. So if I were to call my SBP, and I would just put the number 1 inside of square brackets behind it, it says give me back element number 1. And the first element that we had in there was just the 120. And we see the 1 next to it. That was 120. But what if I wanted the first 3 ones? Well, I just use this colon symbol, 1 colon 3. It says 1 to 3, 1, 2, and 3, a little range operator. And that gives me the first 3 back. If I only wanted number 1 and number 3, I'd have to pass that as a list. And remember how to create a list? Yes, they are arguments to the C function. So C 1, 3 will give me back, then inside of this set of square brackets, which means addressing, I'm going to get back just the 120 and the 110. That was element number 1 and element number 3. So in short, that is addressing. Addressing gets a lot more complex. So let's move on to distributions. And what I really want to do here is to show you how to generate your own data. Now, when I use a new computer language, when I learn a new computer language, I just want to play around, and I don't necessarily have or want an actual data set. that I might have lying around. When we have data sets on patients, we keep those very secure. We are diligent about that, and we don't use it to play around with. So we generate simulated data, and that is what we use as a teaching tool. So I want to show you how to generate your own data. When you learn a new language, when you just want to practice, just generate your own data. The beauty of generating your own simulated data is that you have absolute control over it, so that you know when you do the analysis on it what to expect. And it also, when languages upgrade, so in some of the other languages that we have, for instance Julia, in which you can take a course on Coursera and get a certificate from the University of Cape Town. Julia changes, it's a new language, and it's just gone over to version 1.0, so many things change. And when they do change, I just want to test things out, so I would generate a new simulated data set that I can play with. So let's generate some data, and we're going to do that using different distributions. So first of all, let's just look at the uniform distribution. Remember, that is when I have a numerical data set or a categorical data set, and every value in that sample space, every data point value in the sample space of that variable has an equal likelihood or probability of being chosen. So the first thing I want to show you here inside of this code chunk is this set.seed function. And I've giving it an integer argument. You can just use 1 or 1, 2 or 1, 4, 5 or 1, 2, 3, 4, 5, 6, it doesn't matter. If you use this same number every time, it means if you rerun this code, the same random numbers will be generated for you. So if you were to run this code, you're going to get exactly the same. If you used 1, 2, 3 like I have here, you're going to get the same pseudo-random numbers. So I'm going to create this computer variable called age, and then I'm going to assign to that this list object. And to create this list object, I'm going to use the sample function. The first argument is not a keyword argument. It just says, give me the range of values that I can select from, the sample space for this variable. And it's 18:85. That's a range value. So it says from 18 to 85. I didn't put a step by. Remember, like the sequence, we had start and stop and end. Start and from, end and by, from, to and by, I should say, as keyword arguments. And then the by was 2 we used. By is 1 as default, and I can also write it in this way, 18:85, so that's 18, 19, 20 to 85. That's the sample space. Comma, the next argument that it expects is the number of values that you want. And I want 500 values, please. And now I say replace equals true, and true inside of R is all true and false is always all capitals. You can also be a bit lazy and just type uppercase T for true and uppercase F for false, but I like to type it out, true and false. And it says that if you choose a number, say 27, and it then throws that 27 back into the bowl so that when you choose that random, next time that 27 is available again. If you didn't say replace as true, that 27 was not available for a second choice, and that might be, you might want to do that. And here we're just going to say that equals false. So let's run that. We now have an age variable that's got 500 values in it. Now look at my environment here on the right-hand side. We haven't spoken about that. Remember when we created SBP and patient number? They are all there. They live here so that we can take a quick peek at them. And there we see age, which we've just done. It says there in the address, there's 1 to 500. So there's 500 values. And look at this. It says int. It means all of the values in there are integers. So it looked at my list object and it looked at the specific elements and it saw, well, they were all integers in there. Great stuff. Let's create the next one, and I'm going to call it before.after. So just imagine you had a study and you measured patients' cholesterol before and after giving them a new drug, and you just want to know what the difference was in their cholesterol before and after this intervention. So that would be one way. So we're going to simulate that according to the normal distribution, and more than that, the standard normal distribution. And for that, I'm going to use the rnorm function. And I'm going to pass a single argument, and that's just 500, meaning I want 500 values. If I don't put any other arguments, it's going to use the standard normal distribution, mean of 0, standard deviation of 1, and it's going to give me back 500 values at random from that distribution. Now, what if I don't want the standard normal distribution? I want a different mean and a different standard deviation. So here I'm going to create an SBP. Now, we've used SBP before. Now, if I reuse SBP, I'm going to overwrite that little piece in memory with new values. So it's overwritten. Again, I'm using set seed 1, 2, 3, just so that when you run the code, you're not going to get a surprise. You're going to get the exact same values as me. Now, look at something I've done here. I've put this R norm with its set of, you see if I hover over the first bit, it highlights the closing parentheses. So there it is. Let's just look at that. R norm, and now I'm going to use 3 arguments. The first one is how many there are, 500. But then there are 2 keyword arguments. Mean equals 120, SD equals 20. Now, SD is standard deviation. So I say, give me a normal distribution with a mean of 120, a standard deviation of 120 for mean, standard deviation of 20. Give me 500 values back from that distribution. But that's going to give me 6 decimal values, and I don't want 6 decimal values. I just want no decimal values. So one way to go about that is to pass all of this R norm, this complete thing, as the first argument inside of the round function. So the round function takes the values as first argument, and then it takes a keyword argument, digits equal, and then that means decimal places. So in this instance, I want no decimal places. So it's going to give me these 500 values of blood pressures, and when we measure blood pressure, it's integer values, there's no decimal values. So when I simulate that, I like to keep it real, and so I put that inside of the round function. Here we create one called CRP, say for instance for C-reactive protein. Again, I'm putting that inside of the round function. This time I want 1 decimal place. And the first argument is this actual 500 values that I want. And this time I want it from a chi-square distribution. So R, CHISQ. 500 values again, second keyword argument, so keyword argument DF equals 2. So 2 degrees of freedom. So let's generate that. And there we go. Now I want to do something else. I'm going to have as my sample space some nominal categorical variables. Very easy. I'm going to set my seed. I'm calling this one group, sample, and instead of a range, say 18 to 85, I actually pass a list of actual strings. And my 2 strings, so that goes inside of the C function. I'm going to call it control and placebo. I want 500 random of those and replaces 2. I have to put replaces 2, otherwise I'm just going to get 2 back once control is taken and I don't throw it back into the bowl for being selected again at random. It's not going to be there and only placebo is left, so I'm only going to get the 2, and the 498 is not possible, the other 498. So I say replace equals true. So I'm going to get back, and if we look up here, once I've executed that, we see group appears there, and it's control, placebo, and it's going to carry on 500 times. And both control and placebo have an equal likelihood of being chosen at every instance. Now, instead of each of them having a 50-50 chance of being chosen, I can actually set the weights. So in this one, I'm going to call side effects. So side.effects, sample again. My sample space is a list of no and yes. I want 500 values, replaces true, but this time I want a probability of being selected. So I'm saying in this same order. So I've got to have 2 values because my sample space has 2 values and it's in that same order. So no will have an 80% chance of being chosen, and yes will only have a 20% chance of being chosen at every iteration of this 500 drawings of samples. So very important there. So we're going to have a very skewed distribution here. So there's going to be many more no's than there are yeses, and we can do that. So we've simulated our own data. Let me show you on the simulated data how easy it is just to do descriptive statistics, and that's up next. So there we go, the descriptive statistics. Now there's a lot of just inbuilt functions built into base R. They've got nothing to do with these extra packages. And here they are. Mean is very easy. It's just the mean. The keyword is just, the function at least is just mean. And I'm just going to pass my list object, which was called age, and that contained the 500 values there. So let's just run that. Remember that came from a uniform distribution. So every value was equally likely to be chosen. And we see a mean of 51.184. Median, well, function's just called median, and the median was 50. The variance is VAR, and standard deviation you've seen before, that's just SD, and you just pass the name for that. Remember the variance being the square of the standard deviation. Range, when we do range, it's going to give us back the minimum and the maximum value. And in those 500, it did indeed choose 18, and it did indeed choose 85, which was the limits of our range anyway. But in this instance, it was. It doesn't mean it would have to be there. This is at random. But in that, using that set seed at 123, if you run this, you are going to get the 18 and 85. Interquartile range, very easy, IQR, all uppercase, and that's going to give me the difference between the third quartile and the first quartile, and that is 33. Speaking of those quartiles, I can get those values back as well. And one of the functions that you use, I like to use quantile. Then I pass my list as first argument, comma, my second argument for the quantile function is what the quartile is I actually want. So the first quartile is equal to the 25th percentile, so it's 0.25, and I get back that value, the 25th percentile value, and then the third quartile is the 75th percentile, so I use the 0.75 as second argument, and I get it there. And if you subtract those two, you get the interquartile range, which is 33, and indeed 33 plus 34 is 67, so that works. Now there's a summary function, and that is just going to give me all of these all in one go. Let me show you. Summary, age, and look at that. I get the minimum, the first quartile, the median, the mean, the third quartile, and the maximum all in one go. That's fantastic. If I write a report or we write a journal article for submission, beautiful. We can just do the summary statistics in one go. I love the summary function. Now, when we talk about categorical variables, imagine that's a large data set. Someone collected it for us. It's thousands of rows long. We don't know what all the unique values are, what the sample space of that single categorical variable might be. Now, we simulated this one. We know exactly what we put inside of group. But if you didn't know and you just want to see what that sample space is, just use the unique function. And that shows us there's only two elements in the sample space of this group variable, and that's control and placebo. But that's the way we designed it. So no problem there. So summary statistics on the simulated data, very easy. And I always say when you are doing healthcare research, medical research, biostatistical research, any kind of research, do descriptive statistics first. You get all this data on a flat file usually, that's a spreadsheet file, even if it's then extracted from a database file. When you look at the large set of columns and rows of data, you don't know what that data is trying to say, what the message is, what the knowledge is that's locked in there. You have to tease it out. And as human beings, the best way to do it is first to summarize it, and we summarize that through descriptive statistics. And then secondly, I love to visualize it, because that visualization is going to give me a great idea of what the statistical analysis is going to show. So describing it first, and then visualizing it. So let's get to visualizing the data. So here we go. As I said, I left lots of space here. Please make your own notes in between. Make this document your own. So the first one I want to show you is just a normal box and whisker plot. So once again, R has got lovely built-in visualization, but you can use the ggplot. I love to use Plotly. There are some videos out already on using Plotly and R. These libraries or packages that allow you just to create even better looking plots. But right here inside of R, plots are fantastic by default. So box plot is the function for a box and whisker plot. And let's just look at the age. I'm going to hit that, and there we go, a beautiful plot. We see our median there, the edges here, first and third quartile, and the minimum and maximum as far as these are concerned. There seems to be no statistical outliers there. And you can see the values here on the left-hand side, and they are written on their sides, and I'll show you how to fix that. I don't like them on their sides, but let's just roll with it for the moment. Now let's just start being a bit more, say for instance, this is going to go on our website, or this is going to be a presentation. Let's just bring some life to this plot. It looks nice to me, I love it, but let's add something to it by some keyword arguments. So I'm going to say box plot, and then age is my list of values, and then comma, my first keyword argument is going to be COL, that stands for color. And the colors, all the colors, there are specific names, and there are a lot of them. So the first one we're going to do is deep sky blue, always inside of quotation marks. These are strings. Main is my second keyword argument, my third argument in this instance, and that means the title. So I'm going to call it patient age. Remember, that's a set of words, so that's strings, so we put them inside of quotation marks. X-lab means the X-axis label, and I want that to say patients, and the Y-lab is the Y label, the y-axis label, and I want that to say age. So let's run that and see what it says. Very nice indeed. I see this deep sky blue color, I see my title there, and I see my x-axis and y-axis titles there, labels I should say. Beautiful, that's quite pretty. Now just a word on this. You see this is happening inside of the document itself, not here inside of the plots. When you do all of this inside of just here, we could have done all that code, and instead of putting each of the sets of codes inside of a chunk, here we can just write the code. But if we wanted to leave ourselves titles, you can't do that here. If you want to leave yourself little comments, you have to put it in a comment line, like we do here. You can't just write normal words in here. So I like to work in here, rather put my code inside of chunks, and then write in between the stuff that I want. But if you did that here, the plot will appear here on the right bottom side. But here in the RMD file, the R Markdown file, it is going to appear right in line. So let's look at histograms. Hist is our function of choice. HIST, it's going to do a histogram. Let's take the before dot after. Now remember, we chose those 500 values at random from the standard normal distribution, so we better see a Gauss sort of curve here. Let's make the color pink. Main is difference in measurement before and after treatment. My x-axis label, my y-axis label, very easy to do. Let's hold thumbs and look at that beautiful standard normal distribution. Isn't it fantastic, this histogram? I just love it. And we see our labels there, and we see our title, and we see the color. What about a scatter plot? Now remember, scatter plot is we're going to have an independent variable on the x-axis, a dependent variable on the y-axis. So each patient will have these pair of values, and we want to have a look at them. The keyword, the function for that is just plot. And we're going to plot the age against the systolic blood pressure. The first one is the x-axis value, independent variable. The second one is the y-axis value, the dependent variable. So remember, you have to have an equal length of those, the same number. So if we had 500 and 500, those pairs, you have to have a value for each side of the pair. We're going to color this just in blue. We're going to have a title, and we're going to have some labels. And there we go. We see a fantastic, nice scatter plot, and we can really see there's no dependence here between age and systolic blood pressure. So I know when I do linear regression or correlation, that's going to be very poor. Age is not a predictor of systolic blood pressure in the simulated data that we created here. So we've created all our simulated data. I don't like to keep it in this format. I like to put it inside of what is called a data frame. And especially when I have a spreadsheet file with actual real patient data, we bring that into R, we can import that. We're going to import that as a data frame. So whether it's my simulated data, I'll convert that to a data frame. And when I import my spreadsheet file with actual patient data, that's going to be imported as a data frame as well. Now, data frame is built into R, but I don't like to use a data frame. I actually like to use one of the newer packages, or new ideas that gives us a tibble. And it's a weird word, but it just means a fancier data frame. So let's just have a look at tibbles. So let's create a tibble from the simulated data that we've had. So I'm going to call my tibble my.data. That's my computer variable name, and I'm going to assign it to this tibble. Remember, that's a package a library that we imported. So tibble is the function, and what it does is you have got to think of this of a spreadsheet file. I'm just trusting that you've seen a spreadsheet file before in your life. The first row is just going to have all the column names in it. And those column names usually for us refer to the variables. So there's going to be age, or patient number, systolic blood pressure, etc. Those are the column headers. And then down that column, we'll have all the blood pressures, for instance, of all the patients. But if I look down a single row, that'll be the blood pressure, age, whatever for that single patient. So have this spreadsheet idea in your head. So what we're going to do here is give the column header or the variable a name. So age, I'm going to write uppercase A, age, and I'm going to assign to that my 500 age list object. And then I'm going to have difference as my second column header, my second variable. And I'm going to assign to that the before.after 500 list object. Uppercase CRP, I'm going to assign CRP, and see why I created those names that meant something to me, and now I'm just using it in a different way that still means something to me. So we see group equals group there, SBP, and now I put S small and BP large. Whatever you want to do. And side effects I wrote all in the uppercase, but I'm assigning those list objects with the 500 values in each to a name that's going to be on the top first row, the column header row of my spreadsheet. But remember, there's not a spreadsheet, this is a table. Let's do that. And now we see my data appear on the right hand side in our environment here. And to the right here we see a little spreadsheet icon, and if I click on that, a new tab is going to open up, very tiny here. You won't see it if you're viewing this not at a maximum 1080p. But there you see it looks like a spreadsheet. There's my age, the difference, CRP, group, SBP. Remember, that's why it set the names. And there's all the 500 values under age, all the 500 values under difference, all the 500 values under CRP. But every row is one patient, for instance. So this patient was 37. Their cholesterol came down because the after was less than the before. There's their CRP value. They fell in the control group though, and they had that blood pressure when they got into the study, and they didn't develop any side effects, for instance. So let's just close that table, but you can always get to that table just by clicking on that little icon there. If you are down here, you could see the console opened up, and what it was actually is the view function with a uppercase V and then my dot data. You can also come and type it in here. Let's do that. And that's going to open the same thing for us here at the top under a tab. So that's the same as that little symbol there. Let's just minimize our console here so we can carry on. So that is our table. Now I might want to share this as a spreadsheet file with someone else. I want to export this as a spreadsheet file. And inside of table, there's this function called write_CSV. Now, please do the following for me as a proper researcher. Never save your spreadsheet files as Excel or any kind of proprietary file format, XLSX. Save it as exported as CSV, comma separated values files. That is a much better way for us to share files with each other. So I'm going to use this CSV file. Now, when you open a CSV file inside of Microsoft Excel, for instance, it's going to look like a normal spreadsheet. One thing that it doesn't have, it won't have all the fancy formatting, and it won't have different tabs at the bottom of your spreadsheet file that you can have different spreadsheets inside of the same file. There's just one spreadsheet per file. But anyway, that is the proper way to do it. So I'm going to, first argument is going to be my.data. That is our actual table that we've just created. And then I'm going to give it a name, data.csv. Where on my hard drive is it going to go? Well, remember we said setwd and then we passed as argument getwd. It's going to put that in the same folder as this RMD file. I set it up that way. If you want to put it in some specific way, remember that you can say C:\\. You actually have to put two backslashes. We won't talk about that. I hate doing that. It just all lives in the same folder. For that matter, let's talk about importing a file. So with Tibble, we also get read_CSV. Now, just in normal base R, that would be read.csv. That's a different function that's going to import it as a data frame. I don't like data frames. I like the more modern Tibble. So I use the Tibble library and I use read_CSV. And I'm just referring straight to this project data.csv file. If you downloaded this from my GitHub repository, that project data file is going to be there for you. And we're going to use that for the rest of this tutorial, and it lives inside of the same folder. So once again, using my setwd and its argument getwd, it's all in the same folder, so I can just bring it in. I don't have to type the address to this file in there. So I'm going to execute this, and there we go. I've now imported a spreadsheet file. So here we exported a spreadsheet file, here we are importing a spreadsheet file. And if you actually go look at your folder structure, this data.csv file is actually now going to appear with the simulated data, and we can give it to each other. Now remember, we imported the DT library. That is a very specific library if you're going to export something to the web as an HTML file. It just formats your data very nicely, and I like to do that when I do export HTML. It has a function called data table, and I'm going to pass data. Remember, that's this spreadsheet file that we just imported as a table. I'm going to do that, and it's going to do this very nice formatting when I export. It actually has a little search bar, and you can go to the different pages until you get to the end. Remember, there's 500, I think, in here. Yeah, there we go. See there, that's the data that we imported. It has 7 variables and 500 each, values for each. So that's slightly different from the simulated one. This is one that I had simulated before and saved before. But it's a very nice way you can search, and you can also just do ascending to descending order there. So very nice. Now that we've imported the actual data set, there we go. Now that we've imported this actual data set, let's just have a quick look at the dplyr dplyr package. It is a bit difficult. I'm going to warn you right now. What it allows us is to extract only certain values that we are interested in from our data. And that's a very powerful thing. But it's not the easiest thing to get used to. And you're going to have to watch some tutorials specifically on this. Here, I just want to introduce you to this concept of extracting data using the dplyr library. So the first thing we want to do here is just to create a new table. Because remember, we used read_CSV that imported it as a table. So we want to create a new table, but we don't want everything from that. We only want to select certain things. And what we want to select is only patients in group number 1. Now let's just have a quick look at this spreadsheet file that we imported. Just to show you, it has an age column. It has a difference column as well. It has a CRP column. It has a group column. And inside of this group column, we see that we have only 1s and 2s, 1s and 2s. So patients were either assigned to group 1 or to group 2. And what I want to do is only extract the patients that were in group 1. So how would I go about that? Well, first of all, I've got to give this new table a name, a computer variable name. And I'm going to call mine control.group, because imagine the group 1 patients were in the control group. So now you see something very funny going on here. I want you to ignore that. Let's just go to this line 325, because this would be one way to write it. Now see it as a comment, and if I uncomment it and we comment this one, so that line won't be executed, the second line will be executed. So let's start with this one. I'm going to use the filter function, and it just says filter row by row. That's what this thing does. And the first argument is, well, what table are you referring to? Well, I'm referring to the data table. And then the second argument, let's just put that on its own line. It says filter group equals 1. Now you see the 2 equals sign. That's called a Boolean operator. It asks a question. Is that line, that row, does it contain a 1? And that will return either a true or a false. If it's true, it will be included. If it's false, it will be excluded. Now this is not the normal way in which we write it. We use that little symbol there. Let me comment out this. Let me bring this, comment this line out as well. We've got to comment out line by line. So let's do this. That is the proper way that we do it. We use this symbol. It's Shift Control M. Shift Command M. It's the pipe operator. We create a pipeline of something that we want to execute. And what the pipe does, this whole little thing, it says, take whatever is to the left of me and pass it as first argument to whatever is to the right of me. And that's just what we had down here. It was data, comma, data, comma. So it just says, take this data and pass it as the first argument. And it doesn't make much sense now, but as you start using it, you'll actually see it makes a lot of sense, especially if you start stringing together a lot of these pipes. So at the moment, it just says, take my data table, go down the group column, and find only the 1s. So if we run that, we're going to create a new table. There it is up there. And if we were to look at that, we'd notice that it's just 1s down the group. There's going to be no 2s there whatsoever. Here's another one that I did, younger patients. So I said younger.patients, go to the data table, and pipe that to the filter function. And what I'm looking for is the age column, everyone younger than 50. So that's going to extract everyone that's 49 and below into a new table. We see the table there, and when you open that, you'll see everyone is younger than 50. Now, this one is slightly more complex. I'm asking here, I want the patients younger than 50, and they must be in group number 1. So again, computer variable name, younger.patients.2, whatever. So the data table, and I'm going to pass that onto the filter function, and I want 2 things. And what we do with 2 things is we put this little ampersand in between them. So strictly speaking, and let me do that right now, I've got to have another set of parentheses there. So it says age less than 50 and group equals 1. So I want both of those in this filter function. Now it's only going to have that patients younger than 50 and only in group 1. And I've created a new table called younger.patients.Roman numeral 2. And as I say, you have to look into dplyr itself. Leave some comments down below if you want videos just on dplyr, but it's a very powerful thing. This is just a very brief introduction to it. Very powerful indeed to tease your data apart and only get the values that you're interested in. Now next up, we're going to look at some more descriptive statistics, this time not on the simulated data that we created one by one, just list object by list object. This time now we're going to extract some of this data using dplyr from our table, and we're going to do descriptive statistics on that. So let's have a look at that. Okay, let's go about describing this table of ours. So the first question we might want to answer is, can we get the mean age of the patients that belong to group 1 and the mean age of patients who belong to group 2? Now we can extract those as 2 different tables first, but we can just use the main table and do that. Let's see how to go about that. I'm going to call my table, that's data, and then I'm going to pipe it to the first function, which is the group underscore by. Group by, that makes sense. And the column which I want the group by to happen is by the group column. And we remember there's patients in group 1, the control, and 2, the treatment arm, whatever the situation might have been. And then I pipe that, once I've grouped them, I pipe that. And you see why I said that these pipes, once we start stringing them together, they actually make a lot of sense. So I'm going to pipe that to the summarize column, summarize function, I should say. And then in the summarize, I want to ask for the mean of the age column. And what we do here is we just give that mean, just a little column name. So I'm just going to say mean.age. That's a name I decided on, and you're going to see why we give that little descriptive name just in a moment. So once again, take the data table, group by whatever you find in the sample space of the group column, and then summarize that for me by calculating the mean of the age column. So let's run this and see what it does. So there we go, we get a table back, and it'll have group here, and it found group 1 and group 2, and then it's going to give me back the 2 mean ages of those 2 groups. And see mean.age there, see we just had to give that column a name, and that's where this little name comes from. So very easily done. So in the next one, let's just see if we group by the side effects. Now some people had side effects, some people didn't have side effects. I want to know how many had side effects and how many did not have side effects. So I just want to count the number of those unique sample space elements. So start with a table, we're going to group by the side effects, and we pipe that to the summarize function again, and this time we are going to use this n function. N open close parentheses, nothing else, and we're going to call that count. What this n is going to do is going to count the unique values. So if we run that, we see count there, that's what we created, and it just does the count for me with this n function. 289 no's, 211 yeses. So you can see when I created this data frame, this spreadsheet file and simulated data before, I gave a bit more weight to the no, not the 80-20 that we did in the beginning. This was slightly more equal. So let's do this. I want to know now how many people in group 1 had side effects and no side effects, and then in 2, how many had side effects and no side effects. Easy peasy. I'm going to say data, I'm going to pipe that to the group by function, and according to the group, and I'm going to pipe all of that, not to the summarize. Now I can do summarize, but count actually will do the count for me, so I don't have to say summarize count equals n. I can just do this all in one go, much easier. I'm just going to say count and then pass side effects as an argument to count. So that's just an easier way to go about it. And now we can see group 1, group 1, group 2, group 2. So group 1 no's was 137, group 1 yeses, 114, group 2 no's, and group 2 yeses. And that is what you need for a contingency table, your observed table for a chi-square test for independence. Easy to extract that information from our table. We have the values there. We can do a chi-square test, as easy as that. So when you have a table, when you've either created your simulated data or you've imported it from a spreadsheet file, it's easy. You can see at least the potential for how easy it is to draw this data out, the values that you want, and just describe them. I do mention though that using dplyr in the beginning as part of what is called the tidyverse is a bit difficult in the beginning, but you'll soon find out that there's a few functions that you use in dplyr, you string them together as a pipeline, and in the end it just makes so much sense, it becomes intuitive to use. After you've described your data, what do? You visualize it. So let's have a look at visualizing the data. Now, these packages work very well together. The table and just the normal plotting inside of R. Let me show you. So we're going to do a box plot, and I want to do the age. So I want a normal box plot of the age. Remember before we just did the age, but this time I want for the different groups, the sample space elements in the groups. So remember they were type group 1 and group 2 patients. And that we just do by creating a little formula, and we do that formula by this little tilde sign. It says, I want a box plot of the age, but please separate it by the group. But now I've got to tell it what the table is that it's got to work from, and it'll work for old-fashioned data frames as well. So I'm going to say data equals data. That's my keyword argument data, and that's my table name data. It doesn't matter that they have the same name. R can figure that out for itself. Color, now I know there was group 1 and group 2. I know there were 2, so I can pass 2 different colors, and it's going to be in that order. And I'm going to do deep sky blue and orange. I'm going to have a table name, a title. I'm going to call that age distribution by group, an x-axis label, a y-axis label, and this time I'm going to use this new keyword argument LAS, and I'm going to set it to 1. And I want you to guess what it's going to do. That's a bit unfair. Let me show you. There we go. Beautiful. Deep sky blue and orange, group 1 and 2, age here. But look at this text on the y-axis. It's all standing up right now. And that's what the LAS equals 1 does for us. It just shifts those numbers so they just look proper. But even isn't that just one of the most beautiful graphs you've ever seen? I absolutely love it. I do like Plotly a bit more, but there's some videos you can watch that I've made on Plotly. Let's make a scatter plot. Remember, for scatter plot, the function is just plot. And this time we want SBP, systolic blood pressure by age. Now, which one goes where? Which one is the dependent variable that's on the y-axis? Which one is the independent variable that goes on the x-axis? There's a little clue for you. The x-axis is the age, and the systolic blood pressure is y. So it's always y-axis, then x-axis. So it's saying, I'm trying to predict this dependent variable by this independent variable. So it's always y tilde x in that order. Everything else being the same, LAS is 1, and once again we see that we don't have this age is not really a predictor of systolic blood pressure there. But with this table, very easy to do that. Let's do some inferential statistics. I'm going to show you the most common statistical test. We're going to start with students t-test. So there's my 2 pound signs hashtag, so that's going to be subtitle H2 size, and then a subtitle with the 3 hashtags, so that's going to be slightly smaller. And then you see I write students and then underscore T underscore. Underscore before and after a word or a set of words or even a paragraph, that means italics. I want that T to be in italics when it's printed out. And if I put 2 of them on each side, that means bold. If I put 2 in front and 2 behind, it's going to be bold. 1 in front, 1 behind, that's italics because I want the T to be italicized. So let's do students' t-test. Very simple to do when you have a tibble. T.test is my function name. I'm going to pass some arguments to it. Here's a list of all the arguments at their default values, so you can actually leave them out. Remember, keyword arguments have default values, so if you don't put them in, those values are used behind the scenes. But let's look at them so you can see that you can set them. I'm going to say, I want you to compare students' t-test. Remember, that is a variable between 2 groups, same variable, in 2 groups, compare the means to each other. So it says, compare for me the systolic blood pressure between whatever you find in the groups. Remember, students' t-test, you can only have 2 groups, and we know group only had group 1 and 2, so this is going to work for us. The tibble, well, that's the data tibble. Alternative, what is your alternative hypothesis? Is it two-sided, two-tailed hypothesis, or is it one-tailed? We want two-sided, and we pass that two-sided argument. Mu is the mean. We expect the mean, our null hypothesis that we create, we want to say there is no difference between the two, so we say mu equals 0. Paired equals false. We can also do a paired sample t-test, and then we just say paired equals true here. But let's, for argument's sake, imagine that there was no grouping, there was no pairing here, so it's paired equals false. And we're also assuming that equal variance is here, so I'm going to say var.equal equals true. So an equal variance unpaired t-test, that's the normal student's t-test, and we're using a confidence level of 0.95, in other words, an alpha level of 0.05. And look at this beautiful result that we get. It says 2 sample t-test. The data is systolic blood pressure by group. We see our t-statistic at 1.4. We see degrees of freedom 498. We see a p-value of 0.15. So it was not statistically significant. We can see the 95% confidence intervals around our t-statistic, and we can see the 2 sample means 125 and 124 up thereabouts. So all the information you need, and really lovely when you start writing your journal articles for submission to a journal. Lovely stuff. Let's do a bit of linear regression. So with linear regression, we build a linear model. The function for that is LM, linear model, LM. Very simple. I'm going to say SBP tilde age. So the first one, again, I'm trying to predict the systolic blood pressure given the age. That is the linear model that I'm trying to build. Data equals data, but I'm putting all of this as a single argument inside of the summary argument. And the summary is going to give me a nice little report as well. And there we go. It says the formula is we're trying to predict systolic blood pressure given the age. We can see the residuals there in our prediction, the descriptive statistics of the residuals. We can see the coefficients there. And we can see right here at the bottom, our adjusted R squared is almost 0. And we could see that from the visualization. There was really no correlation between those two. So really age is not a predictor of systolic blood pressure, and our adjusted R squared is very low. We see our F statistic there. Remember, these things are all built on F statistics and analysis of variance really. And we see a p-value there of 0.12. So really not significant there at all. Very easy to build linear models. If you want to add a second one, it'll just be plus. And then, for instance, we had CRP. So you can just continue adding pluses there, and you'll build more independent variables into your linear model. Lastly, let's do a chi-squared test for analysis. A chi-squared test for independence. Now you can see something else here. You can see it's a level 3 heading here with a £3 or hashtag signs. And then we have dollar and dollar. That allows us to use something called TeX or LaTeX. And that is a mathematical representation of characters. Very beautiful when you print this out in PDF or Word or even on the web. A \CHI means a chi character, the Greek symbol chi, lowercase. And then the caret symbol in 2, that means put what comes next, put that on superscript. So it's going to be chi squared, written out very neatly. And TeX or LaTeX is a language on its own. It's easy to learn the basics and incorporate that, but that's not what this tutorial is about. So What we need is the contingency table. Remember the observed table. How did we do that? I'm just going to redo it here. Data, we pipe that to the group by, and we group by group, and we pipe all of that to a count of the side effects. So let's get those. 137, 114, 152, 197. Pay particular attention to the way this was done. 1122. You might sometimes see no, yes, yes, no. So when you do build your contingency table, make sure that you put the order of the values, that is always the same. So the way that I like to do it, I'm going to create two lists. The first one is my group 1, that was 137 and 114, and group 2 was 152, 97, and I'm going to say the number of rows is 2. There's going to be a group 1 row and a group 2 row. And then what I want to do is to create a matrix. So this is what we use, a matrix function. I'm going to pass some arguments. The first one is a list object, C, and I'm going to pass the first row is group 1, the second one group 2, and the number of rows, n row is my keyword argument, and I'm passing that n rows to it, and that was 2. And I'm saying by rows equals true. Now, you don't have to do all of this. This is just some fancy eye candy that I'm building here. Once that is done, I'm using the row names function. I'm passing an argument to it, and I'm actually making this out to be a computer variable. That's something very specific to R, and just go with the flow. I'm going to put a list object to that called group 1 and group 2, and then I'm going to use the call names function on my matrix that I've just created, and I'm going to put no yes to it, and then finally I'm going to call this matrix that I created. Now you don't have to do all of this. It just produces this nice little table so that when I do share this with my trainees who don't know a lot of statistics, it's just a nice visual representation of that. What we actually only need is those numbers 137, 114, 152, 97. That's actually all we needed. But you can always just refer to this code, create your nice little table as we can see there. We can all see what that contingency table is all about. And I can pass that whole thing with its names that I put in here, the row names, the column names. I can pass all of that to the chi-squared.test function. I don't want any Yates correction, so I'm going to say as my second argument there, correct equals false. And let's run that, and there we get a Pearson's chi-squared test. We see there 1 degree of freedom, and we see our chi-squared value there of 2.1402, and the p-value of 0.143. So really the group and side effects, they were not dependent on each other. And that's it. I hope you like R, and I hope you want to use R, and I hope you have a good understanding now of what it was all about. So let's save this document. So very lastly, I want to show you how I created that final document that we uploaded to our pubs. And what we're going to do is you see a tiny little button here, knit. Let's click on knit, and we're going to wait a few seconds, and it's going to knit from the knitter package. It's going to knit all our code together as a beautiful HTML file. Remember we set TOC to true in the beginning, so we have our table of content of all the headers that we use, the 2 and the 3 little hashtags, built that all together for us nicely. I can click any one of these, it can go down. There's the logo that we put in. You see the colors, our navy blue there for the title. That was in the YAML right at the top, remember? And then our second level headings, they were all colored this gold color, they're all there. And there's all our code and the beautiful execution of that. We see our plots there, absolutely fantastic. And because I've published it before, it'll actually say republish here, but if this is the first time you haven't published it before, you can hit that publish, and that's going to allow you to open a free account on our pubs, and then open up a page where you can give a little description to this file and a name to this file, and you will have your own rpubs website. You can also open this in the browser right here, and that is why I like to not do this as a script, but I like to create these RMD files. You see there's a tiny little down arrow there next to knit, and this, remember I said we can overwrite what it's exported to, because here we can do knit to PDF and knit to Word as well. Fantastic. I hope you enjoyed this tutorial. Let me know in the comments down below if you want to see more about the specifics. Before I recorded this video, I actually put some Plotly videos out there and 1 or 2 other tutorials on R. Have a look at those. Those will all be in the same playlist. and I hope over time to have some time to make more tutorials on the use of R for your statistical analysis.